Good morning everyone. My name is Neha Kadu. I am a PhD student in Department of Management Sciences, IIT Kanpur. Today I am going to present on Digitalization framework for real-time large-scale production scheduling. This is the outline of my thesis. In chapter 1, I will be um, covering the literature review of job shop scheduling problem. In chapter 2, we will be explaining timestamp generation algorithm and scheduling using Osterod matrix. In chapter 3, we will be discussing about scheduling using timestamp list algorithm, and we will also compare it with the Osterod matrix. In chapter 4 is about scheduling using block and slot algorithm. Chapter 5 we will do analysis of timestamp list algorithm and block slot algorithm in different scenarios, and at the end we will be discussing on results and conclusion. Scheduling is defined as allocation of resources to tasks over a given period of time to optimize one or more objectives, and the objectives can be minimize earliness, lead time and tardiness. In our work, our objective is to generate a just-in-time schedule. That means to minimize all the above three objectives. Here is a setup for job shop scheduling problem. There are n jobs to be scheduled on m machines. A job requires a number of processing steps, that is operations. Each job has its own predetermined route to follow. Each operation can be processed by at the most one machine at a time. Each machine can process at the most one operation at a time, and preemptions of jobs is not allowed. Characteristics of job shop scheduling problem. Generally, job shop scheduling problems are NP hard. That means the scheduling problems do not have a polynomial time algorithm, and only special cases that involve only one or two machines may have optimal solutions. For example, branch and bound, shiftal bottleneck, etc. Approaches to solve job shop scheduling problem can be divided into two broad categories, such as exact methods and approximate methods. Exact methods such as branch and bounds are designed to provide optimal solutions, but they cannot be used for large-scale problems. Approximate methods provide good solutions, and also they are suitable for large-scale problems. Some of the examples of approximate methods are uh, shifting bottleneck, local search, and dispatching rules. In our study, we are using the dispatching rules. Dispatching rules are the heuristic to generate solution based on the scheduling environment. It selects the next job to be processed from the set of jobs that are waiting in a queue. Some of the examples of dispatching rules are first come, first served, earliest due date, shortest processing time, slack, etc. In previous studies that uses dispatching rules do not consider uh, the challenges we face in a real life scheduling, such as Dipler and Thompson's use dispatching rules, but it cannot be directly used for the large scale problems. Some studies also considered shift constant, but that involved only 700 jobs. Other studies involved operations up to 1 lakh. In a large-scale production company, there was a challenge in designing a scheduling algorithm that had 6 million operations and then quarter million jobs, and each job varies in terms of number of operations, precedence relations among the operations, release and due dates, resource requirements, etc. And there was a necessity to generate a schedule in less than an hour. So we addressed this problem in our research work. Steps involved in scheduling operation are: we determine the processing time of an operation, the resource that is required for processing an operation. Then we had to identify the next available good slot using a calendar honoring the shift constraints, and also we need to update the resource quantity. The major bottleneck in large scale scheduling problem is that to find a good slot for operations, as the resources are limited and many operations are to be scheduled on limited resources. So this problem is not addressed in previous studies, but it is very important because this finding a valid slot takes much time in overall runtime of an algorithm. Here is the dataset that we are working on. Each job has multiple operations to be performed. Each operation uses a resource. Each resource is available on a particular calendar, and each date in a calendar has shifts. And here we are working on four type of resources. Type 1 and type 2 are the resources that are available in shifts, and type 10 and type 20 are the resources that are available 24 hours. Here are the constraints of a problem. Operation 2 can only be performed after the operation 1 is completed. There are working days and non-working days in a calendar. Operation can be resumed after a break, but it cannot be resumed if the resource is unavailable. These are the steps involved in scheduling algorithm. Initially, we generate a timestamp for each resource. Then we calculate the priority of each job based on some dispatching rule. Then we generate a valid schedule for each operation in a job. And lastly, we update the resource quantity and timestamp. In timestamp generation algorithm, we generate a timestamp from the calendar and resource data. So we represent it in this way. So like we can see at 8 o'clock the quantity available for the resource is 3, and we denote the shift break as -1, and so on. So for prioritization of a job, we use the dispatching rule critical ratio, and the job that is having the least critical ratio will be processed first. So once we generated the timestamps for each resource, the next step is to store the timestamp in different data structures. Here we first started with using Osterot matrix, as this is the widely used matrix for slot scheduling. Here the time is divided into slots, and Boolean value indicates whether the resource is available or not available at a particular slot. But the data set that we are working with have multiple quantities. Also, we need to maintain the availability of resource at every minute, which is infeasible as the calendar span is over 2 years. Here we modified the Osterot matrix and stored the timestamp that we have generated in the matrix and also corresponding quantity in another matrix, but updating the quantity is computationally expensive as we need to shift the entries to the right cells in order to update the timestamp and quantity, which will be very computationally expensive. Hence we came up with another way of storing the timestamps as array list. So uh, this is the initial timestamp that we have. As we can see, at 8 o'clock the available quantity is 3, at 12 o'clock is the shift is starting, and so on. Suppose an operation with release date 1st of January at 10 o'clock comes in, and the processing time required is 120 minutes. So we have to schedule the operation on this resource. So it will start at 10 o'clock. So the available quantity at 8 o'clock will be 3. So we need to add a new timestamp at 10 o'clock with the updated quantity, and the remaining timestamp is same. But suppose if the release date of an operation is at 10 o'clock and the processing required time is 240 minutes, then we can see that first 2 hours of the operation will be allotted from 10 to 12. At 12 o'clock there will be a shift break. Then the processing will start from 1 o'clock, but we have only 1 hour, as at 2 o'clock the quantity becomes 0. That means only 180 minutes we have for processing, and the operation is not fully processed. So in this scenario, the entire schedule that we have generated over here is erased, and we have to search again for a next suitable slot. This shows in detail how the timestamp list algorithm has been implemented with type 10 resource. It also considers if the release date is falls between the shift break or it falls before the shift break, etc. We will not go in detail uh, in explanation of this algorithm. This shows for type 2 resources and updating the resources that we have already seen. So the limitation of the algorithm is that when any resource is highly occupied with many operations and the quantity is very less, so there will be many unsuccessful searches which will increase the complexity of the algorithm. In order to overcome this problem, we come up with another algorithm, that is block and slot. In this algorithm we use tree maps for storing the timestamps. As we can see, the block contains many slots. Each block may contain shift breaks, but in each block resource is always available. And another thing is the job cannot be processed across multiple blocks. So here is an example of a block and slot. We can see BST is a block start time. This block starts from here and it ends till here. This is the block end time. It is including the break. Whenever the resource is unavailable over here, another block is created, and this is the block start time of a second block, and so on. In order to implement this block and slot algorithm, we maintain the two data structures, that is block and slot. This block data structure is a nested tree which maintains the overall details of a block, such as block start time, block end time, and block duration. So in this tree map, the primary key is the processing time. This will be the unique processing time across all the operations, and across the processing time we store the details of the block, such as block start time, block end time, and block duration. So initially there is only one block which we store across the highest processing time, and as the scheduling progresses, whenever the quantity of the resource is 0, we split these blocks, and based on the block duration we place the blocks across different processing times. So blocks whose block duration does not exceed the processing time is placed across the processing time entry as the scheduling progresses. So we will have multiple blocks that will be processed over this unique processing time, which will uh, help us to reduce the search time of finding a valid slot in this algorithm. So once we identify a valid block, the another task is to find the valid slot. So this data structure maintains all the slots in a corresponding block. So we can see that block start time is a key which contains another tree which has slot details. So SST is the slot start time, SET is the slot end time, and slot availability. So this is also a tree, and that means that these times are stored in ascending order. This figure shows how the slot data structure is actually stored. So here we can see that slots are stored in ascending order and the blocks are also stored in ascending order. So it will reduce the search time of finding a valid slot. So due to time limitation, we have not included the detailed implementation of block and slot. So here are the results. We have run the instances. We have run the algorithm for 3 instances. The first instance has zero point 0.1 million operations. The second instance has 2.6 million operations, and the largest instance has 6.24 million operations. So for the runtime for the timestamp algorithm is zero point 0.6 minutes. For instance 1, it is for 4 minutes for instance 2, and 50 minutes for 6.24 million operations. The runtime for roster of matrix is 6 minutes for instance 1. Uh, we have not we cannot implement it on instance 2 and 3 as these are very large instances. So creating such a large matrix is infeasible, but we can observe that the runtime has significantly reduced in timestamp uh, algorithm. And the runtime, we have also implemented the block and slot algorithm for the smaller instance which has around zero point 0.1 million operation and the runtime is zero point 0.9 minutes. Uh, we are yet to run it on a larger instances, so we are still working on it. So after running the block and slot algorithm for larger instances, the another task will be the analysis of timestamp list algorithm with block and slot algorithm in different scenarios such as quantity of type 2 resources available or number of shifts per day, number of unique processing time per resource across all the operations, and external date. So we will be examining which algorithm works better for what particular scenario. So we have designed a set of algorithms for large-scale job shop scheduling problem, taking into consideration the resource availabilities across calendars, working shifts, etc. We have introduced the concept of data structures for real-life large-scale scheduling, and we have used the Austerlot matrix as a benchmark in our study. So in our study, we have used the single dispatching rule, but we can use multiple dispatching rules based on the real-time deviations and different floor conditions using artificial intelligence and machine learning. And the processing of an operation may require multiple resources. We have considered that one operation requires only one resource, but it might require multiple resources, and that too with different working shifts. So this problem can be addressed in future, and we can also consider the interruptions that are caused due to maintenance or unavailability of the worker. So these can be incorporated in the future research. These are the references. Thank you.